Welcome. Let's get started on our first video this week where we're going to introduce an idea known as strong induction. So strong induction is this principle. So it starts off just like normal mathematical induction, P1, P2, P3 are statements that they're true or false for all the natural numbers. They can start at P0, they can start at P1, they can start whatever. We say P1, again, I'm saying P1, it might not start till 4 or 5, but you get the idea. And then for all values in the natural numbers, for which this is true, if Pj is true, if there is a j such that all the values up to j and including j. So this is what I'm saying. If Pj is true for every value up to k, then Pk plus 1 is true. So k, normally we picked k, and we said if Pk is true, then Pk plus 1. Now we're letting everything be true, not just the previous case, but all cases all the way down. This is called strong induction because we're actually going to, it's a stronger approach, but it's also weaker in a sense because you are essentially having to give more criteria in order for this to be true. And so your proof has some limitations on it. So let me look at an example. I actually labeled these in the video, so maybe that'll help differentiate a little bit, make that a little more clear for all of you. So here's a sequence of numbers. I have 1, 3, and I have a sub n equals 3 a sub n minus 1 and minus 2 a sub n minus 2. And I want to say that this formula is true for all values bigger than or equal to 3. I want to prove it's true for all n that are bigger. So here's the key, here's where we can kind of get funky. So first, let's start with our base case. In fact, it's not base case, it's going to be base cases. And I'm actually going to undo that. It was on red for some reason. I apologize. Let's go here and let's go base cases. Our first base case is obviously n equals 3, in which we have a sub 3 is equal to 3 times the previous number, which is 3, minus 2 times 1, which is equal to 9 minus 2, which is equal to 7. But my claim is also this. So I then have to do 2 to the third power minus 1 is equal to 7. These are the same. Check. However, here's where it gets to be a catch-22. I don't just have to show it for this. Again, I have to show it for 2 cases. And the reason being is I'm relying on the 2 prior cases. So I have to show if it's true for at least 2 cases. N equals 4. Well, a sub 4 is equal to 3 times the previous number, which is 7, minus 2 times the previous number, which is 3. 2 more, which this would be 21 minus 6, or in other words, 15. Another claim is that 2 to the fourth power minus 1, which is 16 minus 1, which equals 15. And boom, again, we have the same ones. You can even check these numbers, by the way. These two also happen to satisfy it. That first one is 2 to the first power minus 1. The second one is 2 to the second power minus 1. So we have multiple things that do it. So now we have to do our induction hypothesis. And again, our induction hypothesis has to be very, very generalized. So our induction hypothesis is suppose a sub n equals 2 to the n minus 1 for all n less than or equal to k. So notice I'm saying that it's true for all of them. So now we have to do our induction step. And that's to consider n equals k plus 1. Well, all we know is that a sub k plus 1 is equal to a sub k, 3 of those, minus 2 a sub k minus 1s, But by our induction hypothesis, these equal this one's 3 times 2. I should just put parentheses. 2 to the k minus 1 minus 2 times 2 to the k minus 2. Sorry, this should be k minus 1. Which, again, I'll just keeping it on the same screen so I'm not having to get a new screen. I'm going to multiply this out. It's going to be 3 times 2 to the k minus 3 minus 1. 2 to the k minus, which would be plus 2. So this value, the reason this became 2 to the k was because I multiplied 2 times it. And so that made that portion go away. Well, notice if I group this together, I have 3 times 2 to the k minus 2 to the k minus 3 plus 2. Well, this portion we know is minus 1. That's easy. And this portion, this is really a 1 times this. So this is really 3 minus 1 times 2 to the k. Or in other words, 2 times 2 to the k minus 1, which is 2 to the 2k, 2 to the k plus 1 minus 1. And we just showed that our formula is true based on the previous two situations being true. And so we did induction, but notice I had to rely on the previous two cases. I really had to use those, and that's why I had to say it's true for all n less than or equal to k. If I just said n is equal to k, I got this case over here, but I did not get this case over here. So that's why this induction is a little bit different in where it comes from. Now, what I'm gonna do is, Cameron, you now have the next one, which is this. This is gonna be very similar. A1 is 3, A2 is 5, and A3 is 9. But now notice I gave you A2, AN is 2 times the previous term, plus A to the n minus 2, minus 2 times A minus 3. And then you're supposed to show that's equal to that for the general formula. Think about how many cases you have to work through, and then use your strong induction. Jackson, we'll give you this one, which only has 2 terms, A1 and A2. But this time we're showing, and I know we already know what the formula is, but don't worry about that. I'm showing this is always smaller than 7/4 to the n. That is my claim, is that that's smaller than 7/4 over n. So it's an inequality. You have to use that to your advantage. Alejandro, you're going to do a sequence of numbers. A1 is 1, A2 is 2, and A3 is 2 as well. But now, oh, sorry, that should be a minus right here. I apologize. That should be a minus symbol. You're going to work through that and show that that is less than 2 to the n for any n power. So all of you have a different kind of one where we're doing some kind of recursive. Now let's talk about another application. What if I make this claim that every amount of postage that's at least 12 cents can be made from a 4-cent stamp and a 15-cent stamp? So let's look at this first off. We need some base cases, just like always. We need some base cases. My claim is that it's possible. Well, here's another way to also think about this. I'm saying that for any value n inside the natural numbers, if n is inside the natural numbers and n is bigger than or equal to 12, then n equals 4k plus 5j for some j and k in the natural numbers, because it could be 0, natural, not integers. They could be 0, but we don't want negative because there's no such thing as negative stamps. So that's where this one gets kind of funky. So our base case is, let's go 12 cents. Obviously, this is equal to 4 cents, 3 4-cent stamps. Let's look at 13 cents, and maybe we'll see a pattern here. Well, this would be equal to 2 4-cent stamps plus a 5-cent stamp. 14, 4-cent stamps. I only need one of them, but I need 2 5-cent stamps. Seeing a pattern here, by the way. And next, I come to 15. Would just be 3 5-cent stamps. So we've shown it's possible. By the way, when I go to 16, I'm going all the way back up to this first case, and it's repeating. So I've shown several base cases to be true. Notice I've shown 4 cases to be true. These turn out to be the 4 most valuable cases. All right, so let's suppose, so we need our induction hypothesis. We're going to suppose that for some k bigger than or I should not, I had the wrong directionality. Bigger than or equal to 12. In fact, let's just say it's bigger than or equal to 16 because we just showed that's but I can say it's bigger than 12 that a uh sorry, we can do that. All right, so the frame bigger than the k, every amount of postage $0.12, k cents is possible. Well, now we need to prove the next case. So we're going to consider the k+1 case. That's our induction step. Now notice I show this true for all. So I could put that little word in there, all. Now consider n equals k+1. Well, there's 4 different possibilities. But since I've already shown that it's true, I'm saying it's true, and we've done for 4 cases, then the truth is one of the values value in well, actually, I'm just going to rewrite this very simply. Yeah, what this doing induction. I could do this a direct case, but I'm going to do this with induction. One value in k, k-1, k-2, and k-3 can be written as n equals j for j. With j bigger than or equal to 3, because we already did the size, the 12 case. So because one of these can be written in this form, we know that it, by the way, we only need to do this for a couple of cases, but we can do this for all these. So it can be written as n equals 4j, and then we can replace as many fives as I need, because I have up to three fives. I can replace as many fives as I need to go up that many spots. But let's look at a different option. Actually, I want to do a different way because I realized I could do this. This is the way, but it's not. This isn't as good of induction as the other way. There's two inductive cases to look at. So we're going to break this into case. So we have case one. And that would be that k plus 1 equals 5j for some j. Well, since the smallest 5j in of size at least 5, sorry, at least 12 is 15, which equals 5 times 3. Since this is true, then j is bigger than or equal to 3. Oh, all we have to do then is then 5j plus 1, which is equal to k plus 1, equals 5 times j minus 3 plus 3 plus 4, sorry, plus 1, which is equal to 5 times j minus 3, because I could take j minus 3 and it's still going to be a non-negative integer, because it could be 0, it could be something bigger, but this would be plus 15 plus 1 more, which then is equal to 5 times j minus 3 plus 16, which equals 5j minus 3 plus 4 times 4. So there's ways that we can attack this and actually get this into that form. We just wrote that this form is written in here because case one is that this is a multiple, sorry, case one is that k, I totally messed this one up, is that k is a multiple of 5. In which case we simply took away 3 of the 5s and so forth. So I messed this one up. I suppose that k is equal to 5j for some j. And since the smallest 5j is bigger than or equal to 12, then we can obviously take away 15. We've already shown this is true, so we've already worked on it. And then we can simply say that k plus 1 is equal to 5j plus 1, which is 5 times j minus 3 plus 3. And then we simply distributed and manipulated to get it into the form. So that's our first case. Let me erase that. You can come back and rewatch it. So our second case obviously is that it's not of that form. So our second case, and again, this is an induction. You notice I'm doing induction because I'm using actually k instead of k plus 1. So this one would be case 2. Now I could break it down to all the cases, but instead I'm just going to say case 2, k equals 5j plus 4 m with m bigger than or equal to 0. Not bigger than equal. Strictly bigger than. And we can do this because if it is completely If it is completely, if m is 0, then we have a 5j case, which is just the situation we just talked about in the previous example. So we're simply saying it's equal to this with m is bigger than 0. Well, then what I can literally do is that 5j plus 4 times m minus 1, and I'm going to throw in an extra 5 on here. So I'm going to take away, let me rewrite that. I'm going to go back and I'm going to look at k plus 1. So I have k, I was realizing I could write one, but k plus 1 is equal to, well, it has to be equal to this 5j plus 4m plus 1, which is equal to 5j plus 4 times m minus 1 plus 4 plus 1, which this is going to be simply 5. So this is 5 times j plus 1 plus m for m times m minus 1. So we kind of worked our way through this. That's ugly. I'm going to erase that and make that last line a little cleaner. I apologize. Because I simply broke it off and I regrouped things. And again, I'm relying on the fact that I'm saying that K has to be one of these options. And we showed that it was true for several things and that process would end up repeating itself because we got up to 15. And after 15, it just starts repeating itself in this manner. All right. So I have one last thing for you to do. Let me get this all cleared out. And it's to do a similar one, except suppose that you want to come with N dollars using only $2 bills and $5 bills. This is actually a really good question. So suppose that you were stuck and N is bigger than or equal to 4. So you want to have at least $4. Can you write every single dollar amount just using $2 bills and $5 bills? Suppose you were in a different country and all you had was $2 bills and $5 bills. Could you do it? And this answer tells us we could. May not be pretty, but we can still do it. All right. Good luck. Let me know what questions you have.